So you can see we have L naught, the relaxed length, and then the stretch length of 1 meter down to here, and then I'm going to pick a lens to solve this problem. I'm going to pick the energy lens. Why? The motivation for an energy lens is going to be a conversion of energy, or where work is done. And so I can say, at the initial unstretched length, we can say that there's zero energy in the spring, but I do work that's turned into the potential energy stored in the spring. Now I'm not going to look at that. I'm going to start here. I start with potential energy of the spring, with its stretched energy of the spring. And as I let it go, the spring pulls the mass up, and that potential energy of the spring turns into what? Some increased gravitational potential energy and some kinetic energy as the mass accelerates. And then once we pass the unstretched length and the mass continues to rise, this kinetic energy turns into just gravitational potential energy. And so in the end, all of our stored energy in the spring is turned into gravitational energy. And I'm going to say that zero height is at zero gravitational potential energy is down here at the very bottom, 1 meter below the unstretched spring length. So now that I have this, I can look at what these energies are. This is 1 meter is a spring length, so I can say, okay, 1/2 k delta x squared. This potential energy turns into mgh, and let's call this h relaxation, plus 1/2 mv squared. And this is the velocity at the relaxation point, is equal to mgh max. And we know this elongation length is the same as this relaxed height is 1 meter. So then the stored energy in the spring is 1/2 times 8.8 newtons per meter times 1 meter squared. That's 4.4 times 1 squared, Newton meters squared per meter. One of these meters cancel, and that gives me 4.4 Newton meters, which is 4.4 joules. So the initial energy of the spring is 4.4 joules. Now that's turned into gravitational potential energy plus the kinetic energy of how fast the mass is moving here. So we can find that mghr is 0.2 kilograms times 10 meters per second squared times 1 meter. And we have 2 kilogram meters squared per second squared is 2 joules. This means the kinetic energy must be 2.4 joules in order to equal a total of 4.4 joules that we had stored in the spring in the beginning. And we can solve for this velocity that the mass has right here. And that's equal to 24, and a joule is a kilogram meters squared per second squared divided by kilogram, giving me 24 meters squared per second squared. Oh no, that's the wrong units. Oh right, this is v squared, and so I have to take the square root, which is good because 24 meters per second is way too fast. And so the square root of 24 is a little less than the square root of 25. We're talking about 5 meters per second, about 11 miles an hour, a running pace. But what we really want to know is how high does this get? So we can set this maximum gravitational potential energy equal to 4.4 joules. We can look at this and see this is a force of gravity, and that's the height. Oh, great, force times height, that's work. Work turns into gravitational potential energy. Makes sense. Anyway, the mass is 0.2 kilograms times gravity, 10 meters per second squared. This is just 2 newtons. So the maximum height is 4.4 joules divided by 2 newtons. And we can write this 2.2. A joule is a newton meter divided by a newton is equal to 2.2 meters. So we start down here. 1 meter brings us to the equilibrium. And we would expect this mass then to reach its maximum height 1.2 meters up. Let's see how close we get. 1 meter elongation and the reason we didn't get to the height we thought is because the spring itself has a mass of 180 grams, almost as much as the hanging mass. So we need to consider this. We also would need to consider that the spring itself doesn't start at the very bottom. It starts with its center of mass somewhere in here. Additionally, the weight of the spring itself partially elongated it from the very beginning. So consider all these factors and see if you can predict a maximum height then of about 60 centimeters above the relaxation point. Thanks.